talking about probability distributions, and we'll look into the properties as well as various standard distributions in the probability. So we have random variable x and a column of p of x given to us. So such a distribution is called as probability distribution. And as we talk about mean and variance for a frequency distribution, even for a probability distribution, we can talk about mean, variance, median, mode, and all the measures of central tendency, dispersion, skewness, contortion, etc. But we'll just concentrate on these two measures, mean and variance. And here we denote it by a special symbol called as E, where E stands for expectation. So basically it is defined for a function, and expectation of the simple function x is indicated by this E of x, and it is defined as the sum of the product of all the values of x along with the probability. So you have x, you have px, multiply x and px, obtain the total of that. Whatever you observe total, that comes to be the value of mean of the distribution. That is again based on the definition. Our x bar is equal to sigma fx divided by sigma f, where sigma f is n, and in a large sense, we are sending this n inside the summation or dividing every value of f, and we are calling that as probability. So your mean is nothing but x into probability. In the same sense, so the definition is applied here. And we know variance is given by the formula, or we have sigma square is equal to sigma x square by n minus x bar square. Or if you look into the more general form, it is x minus x bar whole square divided by n, or sigma f in case of frequency distribution. So if I take sigma f inside the summation here, that becomes probability. So I can define variance of x indicated by V of x as expectation of x minus expectation of x whole square. So it's similar to this x minus x bar whole square. So here x bar is indicated by ex, that is x minus ex whole square, which could be further simplified into e of x square minus ex whole square. So you can have a problem on this. A distribution will be given to you. You have to compute the mean as well as variance. Now this expectation in more general is defined for a function of random variable, any function say g of x, and if I say expectation of g of x, that is defined as the total of g of x into p of x. So if you take g of x to be simply x, so you get mean ex, and in place of g of x, now we will just have x. Now the second case, we need e of x square. So if you replace your g of x by x square, you will get e of x square, and the definition of e of x square is total of x square into px. So I have to compute x square, multiply x square with px to generate the value of your second moment, and from that you can obtain the value of variance. Now take this g of x as log x to produce geometric mean, 1 by x to produce harmonic mean, and various other g of x like x cube, x power 4, etc. produces the moments which could be used in obtaining the measures of skewness and cutoff. So this is a more general definition. So if you could understand that, that is fine, or else that is not required. Anyhow, I said we'll be just concentrating on the computation of mean and variance. And I'll take an example problem and let us see the mean and variance of a distribution. So first case, let me say 3 coins are tossed. Obtain the mean and variance of number of heads. 3 coins are tossed. Obtain mean and variance of number of heads. observed. From yesterday's exercise, we know how to create the probability distribution for the case where 3 coins are tossed. So when I toss 3 coins, and if I look into the possible numbers for heads, so let me call this x as number of heads observed in the 3 tosses. Then I could observe the different values of x as 0, 1, 2, 3. And if you look into the sample space, you remember there are 8 cases because we are tossing the coin 3 times. So when you look into the probability, x is equal to 0 indicates all are tails. So it is 1 out of 8 case. So probability is 1 by 8 or 0.325. When I say x is equal to 1 head happen in the case of HTT, THT as well as TPH. So 3 out of 8 case probability is 3 by 8 or 0.375. Similarly, x is equal to 2 takes the probability 0.375 and your x is equal to 3 also takes the probability 0.125. And to check whether you have computed the probabilities for any distribution, look into the total probability across all the values of your random variable. Total probability should come to 1. Now for this, we have to obtain the values of mean and variance, and the formula for mean is P of x is equal to, yes?
Sir, kindly repeat P of x.
P of x is probability. What is the probability of observing 0 heads? In 0 heads and that?
3. 0 heads means 3. 0 heads only once.
One possibility. So probability in 1 divided by 8.
By?
Which is 0.
How we got that 8, sir? We have tossed 3 coins.
That is in the question. 3
okay,
coins.
Sir. 3 coins.
Obtain the mean and variance of number of heads. So we have to look at
3 coins are tossed once.
Yes.
Okay, sir.
Yes. Oh, so we got the probabilities. Now, if I look in the definition of mean is E of x is equal to sigma x into px. So I have to multiply the values of x and px and obtain x total. So I'll have 0 into 0.125, 1 into 0.375, 2 into 0.375, 0.75.
Light.
And then 0.375. Oh, so the total of this comes to be 1.5. So we have total of x into px as 1.5. So that is the average number of heads which we could observe when we toss 3 coins. Coming to the variance, now the simplified form is E of x square minus Ex whole square. And to obtain E of x square, I have to apply the formula of expectation. So E of x square is total of x square into px, and E of x is total of x into px. So I need the values of x square and then total of x square multiplied by px. So x is 0, 1 to 3, x square is 0, 1, 4, 9, x square multiplied by px, then 1 into 375, 4 into 375, and then 9 into 375. Correct. So 9 into 0.125. 1.125. 4 into 0.3. So this total comes to 3. So this will be 3. E of x square is 3. So first term is E of x square minus E of x whole square, which is mean. Mean is already computed in the previous step. That is 1.5 square. That will be 3 minus 2.25, which comes to 0.7. So this is the variance of the distribution. So just remember these three columns. Whenever you have been given with the frequency of order distribution, the procedure is same. In case of x and f given, we'll compute f into x, x square, f into x square. In the same way, x into px is given. So we'll do px into x, x square, px into x square. Just the totals are sufficient to produce mean and variance. And because the total probability is 1, so there is no divided by total probability. So this is how we compute mean and variance for a probability distribution. So you could have one numerical problem under obtaining mean and variance of a probability distribution. So please memorize the formula. E of x is equal to total of x px. E of x square is total of x square into px. And we use both ex and ex square in computing the variance as the formula E of x square minus E of x the whole square. So this is how we compute or we study basic properties of a probability distribution. As said here, the probabilities are obtained on the assumption that all of these are equally likely and mutually exclusive. But when it comes to the practical cases, so certain distributions are such that observations or the probabilities based on the classical approach cannot be obtained. In that case, we go to statistical methods. So whatever the cases, for you, the question of obtaining mean and variance will be on a problem where we will give you the values of x and px, or a simple problem on classical approach, like say 3 coins are tossed once, generate the mean and variance for number of heads or number of tails. What are the mean and variance of number of tails when 4 coins are tossed? Or you could talk about the distribution of throw of a die, obtain a mean and variance for the outcome of a die thrown once. So in that case, you are throwing the die once, so the outcome could be 1 to 6, and each of this occurs 1 out of 6 times. So probability comes to be 1 by 6 for each case. So now you do x into px, x square into px, and obtain the mean and variance. Now certain times the distributions could be complex, and when you look into the more general situations of computing the probabilities for a case where, say, you want to talk about a situation where the experiment is said to be taking only 2 possible outcomes indicated by success and failure, then such a experiment is called as Bernoulli experiment or Bernoulli trial. And mathematically, success, we count the number of success. So there is 1 success, there is 0 success. So success is indicated by failure, and success is indicated by 1, and failure is indicated by 0. And we are interested in obtaining number of success, and we could expand this and obtain the repeated cases of Bernoulli, and each and every trial is independent. So this generates what called as a binomial distribution. Okay. So in the last class, we have understood what is a random experiment. A random or statistical experiment is one where the outcomes are different. Every time when you conduct the experiment, outcomes are different and they are random. There is uncertainty. You cannot exactly predict what will be the result. So we are talking about such experiments, and one such class of experiments comes under the case called as Bernoulli experiment. Here we are talking about the random experiment, which has only 2 possible outcomes. All the experiments which have only 2 possible outcomes, and which you can clearly categorize them as success and failure. You give the definition. Whatever may be the outcome, you give one outcome, you will define one outcome as success, the other outcome as failure. Say for example, I could talk about tossing of coin. A coin has only 2 outcomes, heads and tails. So therefore, this come under the Bernoulli experiment. Now I am maybe interested in observing the number of heads. So I call, if I observe heads, I'll take it as success. If I observe tail, I'll take it as failure. Or you can remodel it. If you are interested in observing the tails, then the distribution will be for number of tails. And then you will observe the occurrence of head as a failure. And here you are counting how many tails you are observing when a single coin is tossed. So when you toss a single coin and count how many tails are possible, so you have the number of possibilities for tails as 0 and 1, and you have probabilities of success. And if I say that the coin is an unbiased coin, unbiased coin, that is probability of observing head is same as probability of observing tail, and that is half. Then this is the Bernoulli probability distribution for the number of tails when a single coin is tossed. But often this case is not true. Most of the coins what we observe are not totally unbiased. In that case, if the probabilities are not same, then the coins are said to be biased coins, and you have to use your experimental techniques to obtain the probabilities. That is, you will toss that coin 1000 times, you will see how many times it leads you to tail. Say, for example, out of 1000, it leads you 600 times failure, when probability of head is 0.4, probability of tail is 0.6. So this is obtained by the statistical definition. So in all such cases where your p is not half and the probability is not half, so generally we say it could be any such value indicated simply by p, and the other probability will indicate it by q, which is 1 minus p, because totally there are only two cases. So if this happens and the chance is say p% of the times, the remaining will be 100 minus such cases. And when you convert that into proportion, that happens to be 1 minus p, and we simply indicate 1 minus p as q, or such that the total probability is p plus q is equal to 1. So what we mean here is, so we are talking about a special random variable which is taking only two values, say 0 and 1. And what are the respective probabilities? For 0, the probability is q. For 1, the probability is p, such that p plus q is equal to 1. So this is sufficient for you to understand. So there is an experiment going on which is producing random variable which is taking only two values, 0 and 1, with probabilities this. Now, what are such experiments which you can model under this case? We are talking about gender, we are talking about defective and non-defective, we are talking about examination result, say pass and fail. We are talking about a particular teeth to be considered as a normal or a healthy teeth, and decayed teeth. So you are doing only two classifications, that is success as well as failure. So you define which is success for you, which is failure for you. Accordingly, you can obtain the model. Now, if you repeat this experiment many times, so let me say a fixed case of n times, then this model produces another model which is called as a binomial distribution. So I could mathematically define this binomial distribution as the sum of n Bernoulli cases, sum of n Bernoulli variables, sum of n Bernoulli variables. So there are certain conditions, statistical conditions that we'll not talk about, but in most of the cases that is automatically observed, the conditions are satisfied. So let us not worry about those cases. Now let me see how to define this sum. So I have x1, so it is Bernoulli, it is taking value 0 and 1. Now I repeat this same experiment. I'll take another variable x2, which has again a possibility of 0 and 1. Now if you look into the total x1 plus x2, then the cases for x1 plus x2 will be 0, 1, and 2. Why 0, 1, and 2? Because your first variable might take only 0, second variable might take 0. In that case, you get the x1 plus x2 as 0. The other possibility is x1 is still 0, but x2 is taking 1, therefore 0 plus 1 is producing 1. Third possibility, x1 is taking 1, but x2 is taking 0, therefore the sum is coming to be 1. Fourth possibility, x1 is also 1, x2 is also 1, so that is producing 2 cases. So as said, you will have to think about all possibilities. Now, along with this, if I include the next variable x3, which is also Bernoulli, that is also taking 0, 1, 2, then if you look into various such combinations, you'll have 8 such possibilities, but total production will be 4 different values, 0, 1, 2, 3. Now, similarly, if you consider n such variables, x1, x2, x3, xn, then the sum x1 plus x2 plus x3 etc. plus xn will take values 0, 1, 2, 3, etc. up to n, and this is called as binomial values or the binomial variable values. So this will also have certain probabilities. So we'll see how to generate those probabilities. We'll understand this model in deeper, and you will have a compulsory question of this particular distribution. So no numerical problems are involved, only understanding the model, how it works, and what are the practical applications of this. So let us take this for a smaller case and then observe. So I said the coin tossing experiment is Bernoulli. So single coin is tossed, and we define counting number of heads. So occurrence of heads is called as success here. So my x is number of heads. So what I do now, I repeat this for 3 times. Repeat this for 3 times. Now in the previous exercises, we have understood a coin is tossed, and if it is repeated 3 times, it is nothing but tossing 3 different coins together, or a single coin toss 3 times. So whatever the case, you are looking into the outcome of all the 3 coins, and that is categorized as one particular item for the sample space of tossing 3 coins together. So we already know the probability distribution now. So if I say x1 is the number of heads in first toss, so x2 is another Bernoulli because I'm tossing the same coin 3 times. I'm repeating 3 times. So x2 is again number of heads, but that is in the second toss. x3 is number of heads in the third toss. So each of this x1, x2, x3 could be either 0 and 1. Now when you look into x1 plus x2 plus x3, along with the various combinations of x1, x2, and x3, you will observe. So let me call this total as y and see how the probability of y comes to us. Now x1 could take 0, x2 could take 0, x3 could take 0. So this is one possibility because I'm tossing the coin. If the first toss is also tail, second toss is also tail, third toss is also tail, then each of my x is taking 0. Therefore, the total becomes 0. The next case, first 2 toss are tail, but the third toss is head. In that case, my possible combinations are 0, 0, 1. So it takes 1. So I could have 0, 1, 0 or 0, 1, 1. Then the other 4 cases are 1, 0, 0, 1, 0, 1, 1, 1, 0. It is same as writing your h, 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 p, h, p, h. So instead of writing it as h, now I'm replacing h by 0 and h by 1 and tail by 0. Number of heads I will count not 0. So tail is indicated by 0. So I have 0 heads, 1 heads, 1, 2, 1, 2, 2, and 3. So if you look into the total possibilities, I have only 4 such cases. Now think this as a simple example of tossing three coins together. So if you toss three coins, how many heads possibly you can observe? So if you toss three coins, you could observe 0 heads, 1, 2, or 3 heads. So only 4 possibilities are there. How are those possibilities? Because of this Bernoulli experiment, which is happening in the background. Now, if you look into the probabilities for y, if I'm assuming equally likely, so each of the single trial has probability of head is equal to 0.5, probability of tail is equal to 0.5. So this is known to us because we assume the coin to be a biased, unbiased coin. Therefore, the probability is half. Now, if I look into the probability when the sum will be actually equal to 0. Now the sum equals 0 happens if x1 is 0 and x2 is 0 and x3 is 0. So it is 0, that is probability half and half and half. And when we are looking into the total probability, and when you are talking about the events of happening together, so if this happens along with this and along with this, only in that case y will be 0, and that probability is taken to be half into half into half. The probability gets multiplied because of a theorem called as probability theorem on the intersection, which is called as multiplication theorem. This tells that whenever you are talking about simultaneous occurrence of events, the probability gets multiplied when they are independent. So this intersection indicates happening of both. So the same could be extended for three cases. So you are defining three events A, B, C such that A is occurrence of tail in the first toss, B is occurrence of tail in the second toss, C is occurrence of tail in the third toss. So in that case, it will be tail in first, into tail in second, into tail in third. So the probability becomes half into half into half. In general, if you assume that you don't have an unbiased coin, but all these are, say, Bernoulli, with some probability, say, Q, probability of failure, treat P as probability of success. In that case, this will be Q into Q, which is nothing but Q power 3. So I'm tossing three coins. If you want to observe all the three tosses to be tails, then that probability is Q to the power of 3. Now, using the same technique, you can obtain the probability. So 0, 0, 0, 0, 1 produces 1, or 0, 1, 0 produces 1, or 1, 0, 0 produces 1. So for getting the total of y is equal to 1, you can have three cases of the Bernoulli. And if you look into the probability of each of this, so 0 probability is Q, 1 probability is P, therefore this is Q into Q into P. Even in this case, it is Q into Q into P, Q into Q into P, and this can happen in 3 out of 8 possibilities. So the probability is Q square P, and that can happen in 3 ways, 1, 2, and 3. Therefore, the probability comes to 3 into Q square P. And similarly, if you see what is the chance of observing the total heads as 2, a total heads as 2 can come in this way, 0, 1, 1 or 1, 1, 0, and then the other one, 1, 0, 1. So there you have 2 ones, therefore it will be Q into P into P, Q, P, P, Q, P, P, so which is Q, P square, and that can also happen in the 3 ways. Therefore, it is 3 into Q into P square. And if you look into the last case, 3, there is only one case, so that will be P into P into P, which is PQ. Now, if you look into the total probability, you have QQ plus 3Q square P 3qp square p cube, which is nothing but your q plus p whole cube. So if you remember a plus b whole cube, a plus b whole cube is a cube, 3a square b, 3ab square, and b cube. So the total is q plus p. And from the Bernoulli model, we said q plus p is the total probability for Bernoulli, that is always equal to 1. Therefore, this is 1 cube. And this total is always equal to 1. Therefore, this model can be again taken as a special probability distribution, which is nothing but the sum of the repetitive Bernoulli experiment. And this can be now generalized. So I gave a special case where I'm tossing 3 coins. Now similarly, if I toss 4 coins, what could happen to the values of y? I'll have 0, 1, 2, 3, 4. And if I look into the probability, the first one will be always 0, 4 times. Therefore, that will be q power 4. And then this will be 4. Now just look into the pattern here. So your q is decreasing, the power of p is increasing. So next probability must be q cube and p power 1. For the next case, q decreases, p increases. For the next case, q decreases, p increases. So next we'll have q power 0, which is nothing but 1. So I'll have p power 4. And if you look into the possibilities, so when I say n is equal to 4, 4 coins are tossed, then I know the number of elements in the sample space is 16. Out of the 16 cases, all tails, all heads are 1 case. So they'll have 1 out of 16. Then cases where I'll have 3 Qs and 1 P, that is 1 head and 3 tails. So 1 head and 3 tails could happen in this case. These are those 4 cases. So it is 4. Next, we are talking about 2 heads and 2 tails. So 2 heads and 2 tails can happen in this way, and in this way. So these are the only cases. Sorry, 2 heads and 2 tails, right? So I could have heads, T, heads, T, T heads, T heads. So totally, I can come across 6 combinations for 2 heads and 2 tails. Therefore, 6 possibilities. This is the probability. And the remaining are again 4 and 1. Such that if you look into the total should come to 16. And if you look into the total probability, now this is same as p plus q power 4. Now, in general, if you write this experiment for n cases, in that case, we can say the probability model is NCX, p to the power of x, q to the power of n minus x. So what we have understood here is, whenever we repeat the Bernoulli experiment n times, so Bernoulli is repeated n times, Bernoulli is repeated n times, and we, out of this n, we observe x success. This implies the remaining case n minus x are failures. Now this success could be 0, it could be 1, it could be 2, etc. It could be n. And what is the probability for a particular value of x? That is given by this mathematical form, which is NCX, p power x, q power n minus x, where NCX is the mathematical term used to define the combinational possibilities of selecting x items out of n cases, and it is given by the formula n factorial divided by n minus x factorial, x factorial. So this simply means number of different selections of x out of n. So that could happen in NCX space. So simply to understand, I toss 3 coins. How many 2 heads combination can occur? So if you have this question, the answer is 3C2, which is 3 factorial divided by 2 factorial and 3 minus 2 factorial and 2 factorial. And you know the factorial of a number, right? Any factorial is the product of the numbers from 1 up to the value n. So I have 3 factorial, 3 into 2 into 1, which is 6. 3 minus 2 is 1, 1 factorial is 1, 2 factorial is 2. I'll get 6 by 2, which is equal to 3. So let us understand this. What is this question? 3 coins are tossed. How many 2 heads combination will be there? Now I know the sample space for 3 heads. That is HHP. So these are those 8 cases. Now see how many 2 head combinations are there. I have a 2 head here. I have a 2 head here. I have a 2 heads here, which is 3 out of the possible 6. And that is what this number is telling. So in how many ways you could observe 2 heads when you toss 3 coins. So when you're tossing n coins, in how many ways you can observe success, that is given by NCX, generally n factorial, n minus x factorial, x factorial. So if you remember, I wrote 3 q square p, 3 p q square. So this number 3 was actually counted from the sample space when I explained the simple example. But when in a large case, we could take the help of the mathematical terminologies and equations and then formulas actually. So we can obtain this. Now coming to the actual probability term, which is q square p q p square. Now just understand it simply.